mechanical system. Let's say it's a pure state psi. So its density matrix is something like psi. Okay, and separate the set of separate. So I'm basically going to work towards the definition of this. Separate the set of commuting observables into sets A and B. Okay. So disjoint sets A and B. Okay. So they are a set of commuting observables A and B, like two sets of quantum numbers, for instance. So any psi can be written as a linear combination AB, CAB, AB. Okay. AB is some sets and is running. This summation is running over those labels. So the density matrix by this definition, rho is summation AB, A prime, B prime, CAB, C star, A prime, B prime, AB, A prime, B prime. Okay, I've just substituted this guy inside this. Okay.
Sorry, just
yes.
being precise.
Yeah.
A and B together have to be a complete set.
Complete set, yeah. It's complete set of observables. So commuting observables, complete set, yeah. Complete set of commuting observables. Set of commuting observables. So the density matrix in this basis is basically there are two indices, A prime, B prime, AB, which is CAB, C star, A prime, B prime. So that's the entries of this density matrix. Okay. So define the reduced density matrix. This was the concept which was used all the time. Defined reduced density matrix. Rho A, say, basically by tracing over B. So what is the meaning of that? Rho A, it has index only A prime A, which is basically summation B, CAB, C star, A prime B. So you sum over B, and therefore you are left with the matrix with indices only in A prime A. Okay. Similarly, you can do rho B, B prime B, which is summation over A, C A B, C star, A B prime. So you sum over A here. Okay. So this is the two definition of reduced density matrix. So the entanglement entropy now is easy to define. Basically, it's the von Neumann entropy of this density matrix. So SA for observables of A is basically minus trace rho A log rho A. Similarly, SB is minus trace rho B log rho B. So, okay, this is a set of definitions. So let's get some intuition. So we saw there was this concept of maximally entangled states and so on. So let's get some intuition about this, okay, by considering two state systems. Okay, some examples. So we'll get some intuition before we go ahead. Okay. So say for instance a two-state system, tensor product of two spins basically. So what are the states? What are the complete sets? It's basically up. Okay, so this was A. Let's call this subsystem A and this subsystem B. Okay, up, down, down, up, down, down. Okay, so A is the states of the first system, B is the states of second. So this is A, this is B, second one. So I hope that is clear. And so say let's take a state. Let's take a simple state. Let's look at rho, which is just this state. This is just a tensor product, and see what happens. This is a simple example. Okay. So rho A, basically you have to sum over this B. Okay. Here there's only one state to sum over. It's just that. It's just this. In fact, if you write it down, this is just up, 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 up. I mean, two of these, and they're all one. So therefore, rho A is basically up, up. So this is a pure state. As you can see, it's just one So it's a pure state, and if you compute SA, it is 0. So I hope this is clear. In fact, another example will make it a little bit more clear. It's a more non-trivial example, so that it becomes a little bit more clear. So let's take the state. So you can stop me. Cos theta up, down, plus sin theta down, up. So let's take this state, okay, and then just use our definition of this matrix, okay, and write down. So it should be a 4 cross 4 matrix, right? So let's write it out. The 4 cross 4 matrix. So it's basically, let me write the sort of just to label the entries. So the matrix for many people it might be familiar, but just sort of to get the game going, 0, 0, 0, 0, 0, 0, 0, cos squared theta. So you basically have to multiply this together, the bra and the ket. So cos squared theta, cos theta sin theta, 0, cos theta sin theta, sin squared theta, 0, 0, 0. So if you construct row A now, okay, basically tracing over the second fellow, so you just have to sum these two, right? So you will get basically row A, because you sum over the up of the B and the down of B. So you get basically cos squared theta up. So this is the A fellow, we have traced over, and sin squared theta down. And you can see that that this is, if you compute row, I mean now it is a simple matrix, and you can compute trace row A log row A, and if you compute it, it's maximized. So what is maximized? The SA, which is minus row A trace of row A log row A, is maximized as you would expect at cos squared theta is equal to sin squared theta is equal to half. You can actually compute it because you can just, it's basically lambda I log lambda I, and you can see when it's maximized, when it's equally distributed basically. So when this is half. So this ties in with the fact that, of the maximally entangled state. So for instance, if you look at the starting state, it is the up, down, and down, up entangled with 1 by root 2. Cos theta was 1 by root 2. It's entangled. So, and if you look at, say, theta is equal to 0 or pi by 2, you see it's just a tensor product state, and it's minimally entangled. SA is 0. So this gives some intuition. In fact, SA, if you compute, is equal to, as there was a lot of these numbers, log 2. If you compute this, it will be log 2. This is the degeneracy of this. So one of the basic results you start out with this is that SA, so suppose you have two subsystems A and the B, and the complement A and B, SA equals SB. Okay, so let's try to prove that SA equals SB. Yeah. So totally it's a pure. You start out with a pure state, and then you divide it into two subsystems, and you can prove SA is equal to SB. So let's try.
So maximally entangled state would be both plus and both minus? I mean,
no.
Cos theta sin theta can have same sign or opposite sign, right?
Yeah, at least here, yeah, it can have both. Yeah.
Both are maximally entangled state.
Yeah. Yeah, both of them have original state we start with is always pure. Okay. So basic result. SA equals B. And of course, this is easily seen. Entanglement, therefore, entanglement EE, let me call it EE, is not extensive, which is a property people in black hole physics like, right? So anyway, so let's develop a slight amount of machinery. We'll compute, actually look at trace row A to the n. Instead of just row log A, if you look at row to the n, you see that if you imagine that, though it is integer, if you imagine that it can be analytically continuous, there are arguments for that. If it can be analytically continued, you say that S, you can see that as a simple matter of differentiation. 1. So this is a matter of differentiation, and showing it, you can show that this reduces to the one Neumann entropy. Differentiate this. Similarly, there is something like, SB also has some similar expression. N equals 1. And since developing this thing a little bit, we can, there is another concept, it's called Renyi. Okay, R-E-N-Y, I don't know the precise spelling. Renyi entropy. It's fine, it's almost close to this. SAN is 1 by 1 minus n trace of rho a to the n. You can see that when n equals 1, this is without differentiating. With differentiating when n equals 1, it reduces to the entanglement entropy. You can just expand it. So you see, when you expand around this, term is n equals 1, which is 1. Log, I forgot the log. Log is outside. Log is outside. So if you sort of expand this, you can say that's 1 minus n log trace 1. Okay, because trace of rho is 1 plus n minus 1 rho a log rho a plus dot dot dot, and you see the when n equals 1, it reduces to the entanglement entropy. So the Renyi entropy SA limit n equals 1 is equal to the entanglement entropy. Okay, so that's no trace. Oh, the Renyi entropy. Yeah. Log. Well, this is all. No, I think there's a log, because if you take this log, if you take the log, so this is like log of 1 plus x. So log of 1 plus x is x. So we need to cancel, because it's without differentiating. One of the things is it's without differentiating. Okay. So n equals 1 limit without differentiating becomes, I mean, it's, because you need log 1 plus x is x. Okay. So that's the thing. Or maybe there is some other way. But okay, so it is useful to look at. So let's look at, in this kind of way of decomposing the two Hilbert spaces, the complete set. Let's look at rho a to the n. Okay, let's see how it looks like. So let's look at, I will just indicate, then I'll do it for n equals 2, then you can see the way the pattern emerges. Rho a n is basically, so if you remember that decomposition I wrote down, the rho a, the elements of the rho a matrix was something like C star, A prime B, and the B was summed over, because B was traced. Okay, so let's look at the next one. C A prime, so because it's matrix multiplication, A prime is multiplied to A prime. Okay, then there's a B prime, C A prime, B prime, and B prime is summed. This is the second rho A. Okay, and dot 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 dot. Then there's the last one, C star B, and the B is summed over the next fellow, and there's an A, and this, because of the trace, A is summed over. Okay, so sums are indicated by the same object. Similarly, trace of rho B to the n is C A B, C star A B prime. So now A is summed over, okay, and B B prime are matrix multiplications. So C A prime B prime matrix multiplication, C star A prime is summed over, because that's the definition of rho B, and B double prime, and dot 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 dot, and A, so A is summed over the next guy, and this B is summed here because of the trace. And you can see that if I rearrange this line, bring this systematically here, this can be brought to this, actually. So let me show it explicitly for n equals 2, and then you can try to convince yourself. N equals 2, trace of rho A squared is CAB, C star A prime B, C A prime B prime. So I'm matrix multiplication. This is the trace because of the row A. I mean, I'm tracing over the elements of B. Okay, this is matrix multiplication. So B prime, C star B prime A, and the A is because of the full big trace outside. So you can see that I bring this now here. Okay, so and then I bring the next fellow. So this is equal to CAB, C star B prime A. So now it looks like I'm tracing over A. Then I bring the next fellow, CA prime B prime. I just rewrite it like this, A prime B. Okay. So now it looks like I'm tracing over A. Okay. So this is equal to trace of rho B square. Rho B square. So you can see it happen for arbitrary n actually. So therefore trace A, I think this is called Schmidt decomposition or something. But this is the simple manipulation. So trace of rho A to the n is equal to trace of rho B to the n. So therefore, if you differentiate it with respect to n, you get the entanglement entropy. Therefore, at n equals 1, so let me complete the argument. Trace of rho A to the n is equal to trace of rho B to the n. You differentiate it, and so you have the fact that entanglement entropy of SA is equal to SP. Okay. So, so this is the one of the most important first sort of result one does in the entanglement entropy.
That one
Yeah.
on the reflex decomposition is more general.
It's a more general.
Statement saying that all the non-zero eigenvalues of rho A are equal to the corresponding non-zero
Zero eigenvalues of.
B.
Oh, okay.
The whole spectrum is
Identical.
Actually,
Okay.
I was just going to say that.
Yeah.
Because trace rho to the n must be
Yeah.
equal in the two cases.
Cases.
All the non-zero
Eigenvalues are equal.
For
Yes.
every
Yes. Yes. Yes.
And then you don't need to do the analytic continuation.
Relation. Okay. Okay. Yes. Right. Okay, so this is the one of the first. So in quantum field theory, which I think is where the domain of these applications are for this meeting, usually one would like to do A will be a region, a sub-region, some region, okay? So it will be like some region. And B is the rest. Okay? So that's the general thing. Say in 2 plus 1 dimensional field theories, you'll have, say, some region and the rest, because this is a spatial region, so it's a 2-dimensional thing. And you'll have a spatial region and you will have the rest. Like in 1 plus 1, which is what I will focus on mostly, it's basically, say, the one-dimensional field theory is on a line, so we will talk about intervals and its complement and so on. Okay? And one of the results from this whole definition is that if A is the full system, so then rho A is actually the one Neumann entropy of the whole system. It's the one Neumann entropy of the whole system. SA is the one Neumann entropy of the whole system. So therefore, SA is equal to 0 because it was a pure state. It started out with a pure state, and its complement is also 0 because SA equals SB. So this is something to keep in mind actually. Okay. So remember, it's the whole system. Basically, there was no B. So it's the one Neumann entropy of the whole system. It was a pure state to start out with. So therefore, SA equals 0. Okay. So what? So now another thing which was notion which was used, and unfortunately I won't be able to prove this, is something called strong subadditivity. It was actually proved by Lieb and Ruska in 1973, and it's quite a rigorous. I mean, it's sort of sort of complicated analysis proof. 1973, and as far as I know, they just use assumption of the Hilbert space is separable. That means, as we just saw, it was basically it admits a finite countable basis. So it just assumes that, and no, infinite dimensional, but countable. So it just assumes that and uses a lot of theorems in analysis, and it proves this theorem. So in 1973 itself. With the lattice cutoff, yeah, because if it's compact, you can have this countable any. So let me. Well, they don't say anything about the Hamiltonian or anything. Just that Hilbert space has to be separable. That's it. I mean, there's no assumptions about the Hamiltonian or anything.
To any
Yeah,
state.
yeah. Only that rho should have, like it's a trace class operators, as they say, that is means eigenvalues are positive, they run between 0 and 1, and so on. So that is sort of the assumptions they use, and they managed to prove this. So let me state it in a way which was stated by Hedrick, as far as I know, but maybe there are other people who said it. So we have two spatial regions, A and B, C and D. So strong subadditivity. Okay. So two regions. C and D, spatial region C and D. So basically, there are two inequalities. Okay. So inequality A, SC plus SD. So entanglement entropy on C and D. Okay, which we just defined. Okay, is greater than or equal to SC union D plus SC intersection D. And there's another one. SC plus SD is greater than SC intersection D complement plus SD intersection C complement. So these are the two things. I have seen, I mean, I have not seen it in their paper, but I have seen later on that these are equivalent, but I haven't tried actually to prove it, but maybe they are actually. I haven't tried to prove it, but I have seen statements, not in their paper, but later on, I think, by others, that they are equivalent statements. But let me take both of them at the present. Okay.
It refers to two spatial regions,
Just
but no arbitrary state. It doesn't say anything about what state you take in this
Pure, at least these guys, this Lieb and Ruska, it's for pure states. The original theorem was for pure state.
Yeah, but I'm also wondering that if they don't say anything about Hamiltonian or anything,
I think, yeah.
how do they know what is C and D? I mean, where do you make connection between C and D and the Hilbert space?
Yeah, so what actually they do it in the context of, so they take a Hilbert space H and say it's a tensor product of H1, H2, H3. Tensor product like this. And their entanglement entropies are like tracing over 1 and 2, 2 and 3 and so on.
You get product Hilbert space.
Product Hilbert space. And
you identify H1, H2 and H3 as C, D.
Well, yeah, can do that, but yeah, so they get a slightly different version of this thing, which I will tell soon. So that means they're actually disjoint. The regions are disjoint. In that formulation, this thing is written in disjoint spaces actually, because this will be C, this will be D, and they are disjoint Hilbert spaces. Yeah.
But then there is something which joins them. I mean, there is some full Hilbert space.
Yeah, it's broken into this whole thing.
I see.
Yeah.
Because there is a full Hilbert space because you
Yeah.
define the complement.
Complement, yeah.
Which is of a
Tensor structure, yeah.
With two subspaces.
Subspaces. Yeah, H1, H2, and H3. Yeah, yeah. I will tell this version soon. I mean, I will quickly tell this version soon.
Just to understand.
Yeah.
So suppose I'm in 1 plus 1 dimension, so one dimension space. So there I can define a Hilbert space. So entanglement entropy between different states, right? Different
States.
I mean, just like in quantum mechanics, you showed that entanglement between say rho A or B, right?
Yeah. Rho A and its complement is the same. Yeah.
I mean, in the where was the picture of spatial dimension coming in? The spatial picture coming in. I mean.
Oh yeah, it is just like, so this is just two Hilbert spaces, right? So in the when you talk about quantum field theory, you talk. I mean, the best way to think about this spatial region, at least soon we will see, is to think about it in terms of a lattice. Okay. So you have basically like lattice, and then there are spins. Some spin degrees of freedom, okay, and then you are talking about Hilbert spaces of the sublattice and the complement. That's a way to think about it. So here there is some. We will come to that so that this formulation in the spatial region will become a little bit more precise.
But talk about say entanglement between two states, which are, I mean.
Two states, two regions. Two states, two regions. I mean, you're talking about another interval. Yeah. Yeah, that's the. Huh?
I just have some question to Ashok's
not about the Hamiltonian. I mean, why should the Hamiltonian be important? And
No,
why?
I just said that, I mean, if you just state in this language, right, then what is C and D? I mean, if it's just an abstract Hilbert space, right, how do you identify in that abstract Hilbert space what you mean by C and what you mean by D?
Yeah.
C intersection D. I mean, none of these has any relevance to the Hilbert space unless you have some map, right?
Yeah. So the original formulation, as I said, is in terms of these Hilbert spaces. In the
that I understand.
Yeah.
So you are saying there is some H1, some H2,
H2
which
and
refers to C and D.
C and D.
And then
Yeah.
everything else you call H.
Yeah. SC. That's correct.
I mean, suppose I take an example in which every alternate lattice type,
Yeah.
that's one set.
One set.
There are two sets actually.
Yeah. So
And,
do.
I have spins on this set and spins
Yeah.
on
Two
this set.
sublattices.
So I have H1 and
H2. Yeah.
There are no regions here.
Yeah. Here there are no regions. Yeah. But usually in this whole thing, yeah, you can still compute this. Yeah. 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 That's correct. Yeah. Yeah. So let's use this, and okay, soon I will try to give that formulation. I mean, at least I will mention that the formulation which was written at least by Subrat and Sandeep in that way. So let me first use this a little bit. Yeah, you can show for disjoint spaces. Suppose this is disjoint. Suppose this is disjoint. Suppose A intersection B is 0. So now we'll talk in terms of regions. A intersection B is 0. So you can actually prove that SA minus SB is less than or equal to SA union B, SA plus SB. So this is a part of, of course here, if you can show, so if they are disjoint, this is not there, okay, the intersection of this and the pure state, because this entanglement entropy is 0. So this and this we can prove, but there is something like this also. Mod of SA minus SB, it's like a triangle inequality. SA minus SB is less than or equal to S union B plus S is less than or equal to SA plus SB, triangle inequality. So to sort of get this part as you see is simple for disjoint state. A intersection B is null for disjoint intervals. Okay. So, so to show this part, let's use B. Use B, and let's choose C is equal to A, and B is equal to A union B. And A and B are like that, no? They don't have intersection in common. This is A and this is B. Okay, so let's use this second fellow. If I choose C, so this is a replacement. C is A and B is A union B. So SA plus SA union B. So this is just proving, I mean, something like that. So is so what? What's yeah? So C intersection D complement. C intersection.
You said that D and C are disjoint, right? So that's
Here, not in this one, not in this formulation. In this formulation, it's need not be disjoint.
I see.
In this formulation, they need not be disjoint. It's it's the original formulation where they did. It is actually
So it is
disjoint.
derived from here.
Yeah. This is, I mean, from here, I can show from here, I'll get this. But actually, I've seen it in Lieb's paper, it was the original formulation.
But then you have to show that from there you can get there, right?
Yeah, I haven't done that, but most probably it can be done, actually. Most probably it can be done, yeah. So, so let's see, what did I do?
B and C intersect, then
Yeah,
it's a little hard to understand what one means by
the Hilbert space and so on.
the Hilbert space, right?
Yeah. So I guess at least, I mean, individually each of them makes sense, right? Because SC is some region. And then you separate its complement.
Subspace of the Hilbert.
Hilbert space, yeah.
And
C is
SD also you identify
some subspace. Yes, space. Union D is another quantity. It's some other set. Union D is another set, and you calculate as Union D, and then its complement, and then you calculate its entanglement entropy.
So then C Union D.
C, yeah. So let's do that. Yeah.
Suppose C gives some subspace of the Hilbert space, right?
Yeah, C is C and D. Yeah, here.
So C corresponds to some subspace of the
Hilbert space.
which you call H1.
Is the full Hilbert space. Yeah.
Which you call H2.
H2. Yeah.
And then what is the meaning of C union D?
C union D will be this whole thing, right? I mean,
Yeah, but as a Hilbert space.
as a Hilbert space. I mean, so here I suppose this is tuned in terms of the spaces. I mean, in terms for field theory. So in field theory, it will be this whole spatial region.
Yeah,
Yeah.
so that I understand.
Yeah.
But I'm just saying that without saying anything about whether it's a local
Field theory or not?
I mean,
Yeah.
somewhere that information has to go in, right? That it's a
Yeah,
local,
Local
field
field
theory.
theory.
Otherwise, the regions have nothing to do with the Hilbert spaces.
Yeah. Well, regions so the way I understood it, okay, maybe I'm wrong, was that each of the regions have some, I mean, spins. So each of the regions have some spins. So there is a tensor product of states here.
Okay.
Okay, so let's do it in terms of line interval, so it's easier, right? So we have some spins. So this is the A, C, and some other D.
Yeah, if a field comes
Yeah.
inside,
Yeah. So that's how I understood this actually, in terms of, because again, as you see, the method of computation, this replica trick is most rigorous in this case actually. Quantum numbers, yeah. Yeah.
I can clarify. These results are actually proved without any reference to any physical system.
Yeah.
So they are basically mathematical properties of a certain vector space. And
Yes.
many of them actually started out in Boolean algebra. What are the state of state? Some collections of zeros and ones. And you define
Yeah.
a
So the
space.
vector space that you're considering is a tensor space, tensor product of
Various, yeah.
So define a space by choosing a set of basis vectors,
Okay.
and you can expand the space by adding tensor products, extra components. What is a physical analog doesn't have to be specified at all, but you can
Yeah.
construct the whole mathematical structure, and that's where these results are come from.
Yeah.
So if you assume concavity of some function.
No?
No, yeah. Yeah. This is part of that. Actually, that's what I was going to sort of show next. Actually, it's this is like a generalized version of the concavity. Actually, this thing.
The log itself
Yeah.
is a concave function.
Yeah, yeah.
That's what
Yeah. So if you see this, so if you just put this C intersection D, D was replaced by A union B, and C intersection D complement, D complement. Okay, so D complement is 0, so that's 0 plus, let me just continue, C D intersection, this turns out to be SB. Okay, so I'm doing the second one, so therefore SA minus SB is, yeah, SA union B is greater than or equal to SB minus SA. Similarly, you can play again with this, and you can get this. Okay, so that's sort of the proof of the second. Which one? The other one. Yeah, I proved this. C is equal to. So if you choose C is equal to B, and D is equal to A union B, you will get the other one. You will get SA minus SB. You will get SA minus SB. Okay. So this concavity idea. So let me just sort of indicate it here using the subadditivity. So this version, this part is called just subadditivity. Just this part of the inequality. Okay. So let's do this other one. So again, so this concavity or whatever is just sort of, so suppose C was A union B and D, so I replace it with B union C. Okay, I'll just call those things here and use A. Okay. And A intersection C is 0. Okay. So you get S A union B plus S B union C is greater than S A union B union C plus SB. This was the form which was written before. You just use A.
So that you had to use
C 0, yeah. So they're disjoint Hilbert spaces. Yeah.
Amps don't say that, but I see.
A intersection C was 0, intersection C 0. So that's the thing. Okay. So this in this form, it's actually easy to see. Suppose you just replace them with numbers. I mean, this is sort of heuristic, of course, but I just want to show this is analogous to the concavity kind of relations. So if you replace A union B as numbers like A plus B, to say X plus Y. Okay, so this is just analogous, just to show how this is analogous to the concavity relation. And A is say X minus Y, B is Y, C is X minus Y by 2. If you use just substitute this, you will actually get 2 of S X plus Y is greater than or equal to SX plus SY. So I just replace B.
Yeah, but you got A plus B equal to X plus Y. You that choice A plus B is X.
Sorry? Yeah, A plus B, sorry, by 2.
Oh.
By 2. X plus Y by 2. Yeah, so A plus B and A plus C is the same object actually. Yeah. And A plus B plus C is like Sx and Sy. So this is sort of gives you the picture that is like this concavity relation, because this can be easily translated to something like
C equal to A.
Yeah, C equals A. Yeah, C equals. So this basically can translate into such an equation. And
Amps A was what? Related.
yeah, I don't know amps.
It was already.
Yeah.
Or A was already and C was related.
It could have been
Yeah.
both. I mean, the B was the late radiation.
B was
It was the late radiation and it was appearing twice. So the late radiation couldn't be entangled with the early radiation and the Hawking partner.
Yeah, so that's the thing.
I didn't know this, they don't say it, but I suppose A intersection C. The
Yeah.
interior and the early radiation.
Yeah, we had to get this form, I think that had to be used.
So X, Y are, A with the C, A and C are the same, right?
Yeah.
Then how come A intersection C is 0? Sorry, what I didn't.
No, this is just, you take this and just replace it with numbers. Yeah.
Just a
Yeah, just, this is just to sort of have a, this is actually like the concavity relation. Yeah. Oh, yeah, sorry. Yeah. Just to give, this is just, yeah, so another thing is, of course, you can use this to prove that, use A or B, I don't know. You can actually use this, okay, maybe as an exercise. You can use this to prove that it's positive. Entanglement entropy is positive. You can sort of choose your domains. No, this you just replace with something like x naught minus delta and x naught plus delta, and this will be x naught. So therefore, this is like second derivative, no? In that limit. Yeah, maybe as an exercise, you guys can try that. You can show that it's positive. Entanglement entropy is positive from this thing.
That follows from the definition.
Yeah, but just to play, if you are you want to play it, you can play it again. Yeah. So now, of course, we would want to know how to compute this in the quantum field theory, and what we will do is we will just focus. Maybe Anindya will do the higher versions and so on. So I will just focus on the 1 plus 1 dimensional case. Okay. So how to compute? In quantum field theory. So we will focus on in 1 plus 1 dimensional field theory. In fact, we will be even more specific. We will just focus on conformal field theories in 1 plus 1 dimension. And just to make things precise, as I mentioned before, so consider a field theory on the lattice. Consider the 1 plus 1 dimensional field theory on the lattice. So we have something, 0A, 0A, 2A, 3A, and so on, some lattice. And there are states, like spin states each at each point. So there is a complete set of observables. This is formal now, but you can imagine, I think people who have experience with it, you can imagine it, a complete set of observables. So X refers to the site, phi hat, this is the operators. So some spin states at each site, phi hat X, okay, and eigenvalues, phi of X, and eigenstates as tensor product over X. X are the sites. So these are the things, okay. And say there is a time evolution operator. H hat. Okay, so time evolution operator H hat. And let us just first compute the usual one, the density matrix. Okay, and say it's a temperature T, just for the time being, okay, just to make things a little bit precise. So say it temperature beta. So and we want to compute the density matrix. Okay. So basically, this is a complete set of bases. So the density matrix is a function of two such things, right? Two such, bra and ket. So it's basically a set of indices, I mean, two variables like this. I mean, phi of x and phi of x prime with the curly bracket. So the density matrix is basically some functional of phi, say x. Let me call it just double prime. In fact, you can put a double prime here also, just to be clear. Phi of x prime. So it's just a functional between the two. Okay, so we have because it's you have density matrix, it has to have two entries, and these are the eigenstate entries. So this is the functional of that. So this is basically 1 by zeta. So let's write a path integral formulation basically. So first, this is what you actually mean generally. Okay. And then if you remember how to translate these things to path integral, you will notice that, so formally going over to the path integral, one has to compute the following. I hope you can sort of basically understand this. So there is a path integral over the spins. Let me just write it like that. Okay. And because of the boundary conditions at 0 and so 0, it's evolving 0 to beta. So we have something like phi of x 0, phi of x prime. So there's a delta function. And then there is a product over the delta function, delta of phi x beta, phi x double prime. So you want to impose these boundary conditions at the 2 points, and you evolve it. And of course, when you go over to the path integral, this becomes the Euclidean action. Okay, so SE is basically LE d tau 0 to beta. So this is simple. If you remember a little bit how you convert things to the path integral, this is how it will work out. Okay, so let's and trace rho because of this normalization. It basically imposes trace rho is equal to 1. So that's what that imposes. So let's understand a little bit more in the picture. What is one doing? So basically, we have at time t is equal to 0 some set of states. So we are evolving it. Okay, and so tau is equal to 0, tau is equal to beta, and when we take the trace, we are making them same, so putting them equal, okay, and integrating over them. So that's what we are doing in the path integral. We are evolving it by that Euclidean Hamiltonian, and when we take the trace, we are putting them equal and integrate. So when one takes the trace, let me write. when we take trace, for instance, takes the trace so one sets phi of, like, say, x double prime is equal to phi of x at prime. So those variables to be same. At tau is equal to 0, this is at tau is equal to beta, and integrate. So in a picture way of thinking about it, so because this evolution is also like that, okay, we are integrating over this, okay. So when you think in terms of the picture, it's like swimming towards these, swimming them together, okay, identifying them and swimming them together. So that's one way of thinking about this, okay. So suppose you do partially, okay. So now that is the thing. So suppose you do this partially, meaning we have some region. So that is taking trace rho, okay. But what we are indicated to do for this entanglement entropy is, suppose we have a region. Let me draw another picture so that it becomes a little clear. So we have a region, say A and B. Let me draw it here. Okay. So we are not tracing over some sub-region, right? So this is tau is equal to 0. Okay. So we are identifying these two, okay, and so here in taking trace rho, we are identifying all of them and swimming them and integrating over phi. But here we are identifying only this part and this part, but not this, not this. So it's like it leaves a cut. It leaves a cut. So this doing this operation that is, as I said, described in words, that is swimming together on these edges, but not this. So this, okay, I have said it in words. This evaluates the reduced density matrix of region A. There is AB not swimming together. Now with this picture, it is easy to think of what to do for trace rho A to the n. Okay, so because that was our operational method, how to compute the entanglement entropy. So suppose we want to do rho A to the n. So what we will have is basically, let's write it out a little bit. N times. So we are doing this. Now here, of course, when we do this, there is sum over the indices of A. There is sum over the indices of A. So that's like putting them together and integrating it. So there's another copy of this whole object, this whole sheet, okay, joined here, and then you're integrating it to that next copy, that is this. Then you go on, okay, but then you have to come back. So I hope this picture, this is called the replica trick formally. I hope this picture is clear. It is easiest to think in terms of this lattice picture. I think that is the best way to think about it. Okay. So I hope this is clear. Yes. Yes. Yeah. So here, of course, I'm putting it at temperature T. I mean, yeah. So yeah, not in. I mean, I'm just tracing over subsystem. There's already a density matrix to begin with, actually. Yeah. So this is, yeah. So I will go back to that system soon. I will. This is like useful to introduce this, how to do this replica trick. But I'll go back to the zero temperature case soon, actually.
Also for the number set, is it A and entanglement or A and the complement A?
No, need not be. No. So let's see. So now we have got this picture correct. Okay. So basically, so we sew together. So let me write some words at least. So we n copies of the same path integral okay. So phi of x So let me write it. Tau is equal to beta minus k. So the kth copy, tau is equal to beta minus is equal to phi of x at tau is equal to 0 for regions x belonging to this interval. Let me just call it A fully. This is sort of the boundary condition. K is equal to k plus 1. Sorry. So this is sort of the identifications of this thing which we have to do. And similarly, so there is this periodic boundary conditions. Beta minus means just a little bit below. So this is the last one. This is the last one. So fermions, okay, we are doing thermal. It's actually you have to do antiperiodic. So the last one will be minus sign. Okay. We'll have to do antiperiodic. We'll see that how that comes about. So this is for the bosons, this boundary conditions. So basically we need to evaluate the path integral in this geometry. Okay. So let me just, so to evaluate trace of rho a to the n. So suppose we are interested in evaluating trace of rho a to the n, we need to evaluate the path integral in this geometry. So, so to evaluate trace of rho a to the n, we evaluate the path integral in the replica geometry. It's called, so basically trace rho a to the n is equal to Zn. So this is just called that A is this region. Okay. This is just the notation. And this is the various products of the normalization which keep coming when we do it, Zn normalization. So let me draw one more picture which people might have seen so that it reminds you of some Riemann surfaces. So basically again, so I just draw the full sheet like that actually, instead of like a cylinder. So say there are two cuts, and so we just connect them. There's one more say, and this is connected, it's connected, and so on. I mean, it's just connected. So this, I think, if you see literature on the subject, it will be called Rnn. So n is basically the number of copies. Capital N is the number of these cuts in these intervals. So basically we have to, so if there is some, it's a higher genus Riemann surface, there's a formula for the genus. But let me just indicate for people who are doing holography at least. So this is basically the thing we have to evaluate. Trace A rho to the n, get evaluate. And if in holography basically what it says is that if you have a CFT on some surface, on some boundary, you can evaluate it by looking at the partition function of the gravity. Okay. So basically, if you know the dual of this replica geometry, if you know what's the bulk dual of the replica geometry, you can actually compute this. So these are the sort of modern approaches to compute this rather than the RT formula, as the RT formula will be reviewed extensively in the next lecture. But there is a formula due to Ryu and Taganaki, and the general, this is sort of the more sort of first thing you would do. If you know in field theory you do this calculation, you would actually evaluate the trace rho a to the n. You'll evaluate the bulk geometry corresponding to this. You'll find out and then take the partition function and try to evaluate this quantity. And it has been done, at least in 2+1 case, this can be done quite precisely. Okay. So now let's proceed simplistically for the single interval and actually get the formula. Okay, for a conformal field theory with central charge C. Okay. So we'll proceed. So for the case of obtaining the formula, for the single interval for a CFT with central charge C. Okay, so this is like a simplistic argument. I think this is the argument given by Cardi in one of the StatFiz, I think 2003. It's a little simplistic, but there is a more formal method. But if I go, it becomes a little bit more involved. But I will give you the simplistic method first. Okay. So basically, again, we have said, I'll say this in words, we have to evaluate the partition functions on this geometry. Somehow, if you are able to do that, we can compute trace of rho to the n and obtain the required thing. So trace of rho a to the n. So let me, so we will take beta going to high temperature limit, beta going to 0. Okay. And let's see how the geometry looks like. So basically, it looks like a thin cylinder. Okay. And this length, now I call, this cut length I'll call L. And there is sort of, this, here there is lots of identifications. And, it is sort of, lot of loops are here. It keeps on identifying. And that's how, so the full length is L, say, of the CFT. And we are taking beta going to 0. Okay. So the cylinder shrinks. It becomes like long. Okay. And we are looking at this. So you can imagine from this identification, roughly.
So on a cylinder, it will depend only on the ratio, right? L over beta.
Yeah. Finally, we'll get that soon. Yeah. CFT, yeah. You will get it L over beta. And this is an argument to sort of, sort of heuristic argument to get the answer, actually. But there is a precise argument. So trace of rho a to the n is, so you can think of this as two separate things. Okay. Here we are identifying it n times. So it's the partition function of the interval L, but with temperature n beta, because you are identifying it n beta times. Okay. And then, so the rest is length L minus L beta, and that is just like that. That is just, nothing is there, is to the power n. Okay. Divided by, so this is the normalization, L beta to the power n. Okay. So it's this, there is because of the identification there is n beta. The rest, there is nothing, it's just tensor products of copies because there is no identification there. L minus L beta to the power n. Okay, so it factorizes, and this is the normalization. Okay. Then we can use extensivity of the free energy, because Z, so we are at high temperatures. So Z L beta in the CFT is basically extensive beta times the partition free energy. So it's some extensive quantity f of beta, something like this. So if you plug in that, you basically get the answer Z of L n beta divided by Z of L beta to the power n. You can see that capital L cancels. The capital L thing cancels between these two, and you get this answer. Okay. So now let's plug this. This is equal to e to the power of minus n beta f. So free energy, write it L n beta divided by e to the power of minus n beta f L beta. This Z, this. Oh, not Z1, sorry. ZLN, it was, yeah. For this part of this, small interval, it's because of the identification, this. Yeah. And this one, you use extensivity. So this is e to the power of L minus L. And this is e to the power of L. You use this extensivity formula. So Z of L beta is e to the power of minus beta L times some number, some function of beta.
Right, okay. Right. So I can understand wherever there is a capital L,
it cancels off. Yeah.
But what about Z little l and beta? What happened to that?
I've just kept it as it is. Oh, sorry.
Oh.
Sorry.
Thank you.
Sorry. Sorry. It's a mistake.
So you're assuming that capital L is way
bigger, yeah. Well, it cancels just by linearity, no? E to the power of L minus L. It's extensive. The answer is extensive. Yeah. And this is L minus L like this. Answer is extensive, so it cancels. So this one, so we have this answer now. Now we can use the high temperature formula for the free energies in any CFT, actually. So we can use that. So I don't think I will get anywhere, so I'll just stop whenever the time is up, actually. So we can use the extensivity. So F L beta, free energy of any CFT at high temperature, is basically minus pi CL by 6 beta squared. High temperature. Of free energy. It's 1 plus 1 CFT. You can check this, I mean, many using modular transformation and so on, you can get this. You can see this is from dimensional analysis. L is the extensivity, C is the sort of degrees of freedom. This is the formula. You can just plug this inside here. So you get trace of rho a to the n is e to the power of minus pi by 6 C by beta n minus 1 by n L. You can see how that comes because see this n beta and the other one has n beta squared downstairs, and this 1 by n comes because of that, and here there is n beta, and that's the expression. Okay. So now if you know something about the cylinder kind of CFTs, you know that two-point function of operators of dimension delta, which is say C by 24 n minus 1 by n, is observation. So if you have operators of dimension C by 24 n minus n, so then the two-point function roughly is something like sine hyperbolic pi by beta L to the power of 4 delta, which in high temperature is minus pi by 6 C by beta n minus 1 by n L. You can just check. Delta is the dimension. 4 delta. Oh, sorry. N, let's put.
I mean, two-point function where the operators are kept at the
Two ends, 0 and L. Yeah, so that is the thing, this answer. So this certainly looks like that, and in fact, using that, in fact, you can prove this very rigorously. So I don't know whether you want to hear the argument, but you can prove this quite nicely that these two operators have these dimensions, and you're evaluating the two-point functions of these operators, and you can actually go over to the plane by this conformal map. And if you go over to the plane by the conformal map,
So you get an extensive entanglement entropy here. Now.
here, but in the
Yeah.
pure state, yes. Yeah, that's correct. So if you go to the plane, you'll see the beta dependence cancels off. So you can map to the plane by the, so to map, can map to the plane by L equals, this is the usual map, log L prime. Okay, so this is the map. And in L prime variables, so trace rho a to the n is 1 by L to the power C by 6 n minus 1 by n. Also, you have to, when you do this, you have to do a little carefully about the dimension of the operators involved and so on. I mean, there is a transformation to go to the plane. You just have to implement it correctly. And so you have this answer. So we have calculated the partition function. And so minus del by del n, trace of rho a to the n is, if you put the sort of dimension cutoff, L by C by 3. L prime, sorry. Yeah. I mean, afterwards it became L again. Yeah. So these operators, so you can actually do this more precisely using word identities to show that these operators have this particular dimension. But yeah, I can, maybe I wouldn't mention it. But what one, maybe I. Yeah, these are the twist operators. In fact, for free bosons and free fermions, there is an explicit construction. So that's what I wanted to mention now. So where will I stop actually?
You started at 4:20.
4:20. So.
At 4:25. So
Okay.
just.
So 1 hour.
No, that's 1 hour, but you have.
Half an hour more. Okay. Yeah. So I don't think yeah. So anyway, so for free bosons, this is what I wanted to say. So for free bosons and the free fermions, there is an explicit construction of these operators. And that's quite useful actually to study many cases, in fact. So,
Sorry, Justin. So at what stage did the lattice cutoff come in? So
yeah, that I think
equal to beta over 2 pi log L prime over A.
yeah, maybe here, yeah, the transformation, yeah. So, yeah. So let me, so should I introduce this twist operators? Yeah, that's what I'm thinking. I will just do it for the bosons, and I mean, there are answers for the fermions also. So let me just sort of, if you have free bosons, okay, I will just do it for the free bosons. I think for this, some people should have some knowledge about at least quantization of a free boson or string. Yeah, I should assume that, yeah. Yeah, nowadays that is forgotten, you know. Yeah, it's a free field. Yeah.
More than a free field.
This is a free field actually, free boson. Yeah, for this. I mean, you can evaluate this for the free field, but
Twist operator, you need something more.
yeah, to construct them, but to argue that the weights, we can just calculate the 0-point energy. That is sufficient actually, it will give you the weight. Okay. So, but maybe I will just say it. So, suppose we want to do this for a free boson CFT. So, we have n copies. Have n copies glued along the cut. And suppose I take the cut just to sort of indicate first to the semi-infinite line. What we have is we have this boundary condition phi I e to the power of 2 pi I z. 2 pi z is phi I plus 1. You can formulate it like this, or phi I sigma plus 2 pi is phi I z. Phi I plus 1 z is sigma. In this variable, cylinder variables, you can write it like this. And so this cut, and finally there is a periodic identification. So it's basically the shift matrix. So the identification is brought, if you think of this as a column vector, the identification is brought out by this shift matrix 1. So in the last, it is 1. For fermions, there will be a -1 here. So that's the difference. For fermions, it will be -1. And so this is, and you can go to another basis which is more closer to the sort of orbifold constructions which people are familiar with in string theory. So you can go to the eigenbasis, which is basically phi 1 plus phi 2 phi n, phi tilde. So these are the copies, I'm labeling the copies. Phi 1 tilde is phi 1 plus, it's basically a discrete Fourier transform. And so on. This is 1, and then there will be 2 here, and 2 all, there will be 3 here, and so on. Okay. So this shift operator in this basis basically acts like this: phi tilde sort of k sigma plus 2 pi. So phi tilde k sigma plus 2 pi is e to the power of 2 pi I k by n phi tilde k. So this is more familiar to people who do orbifold CFT. So this is sort of a twisted boundary conditions. So if you go around the circle, you pick up a face. So it's a complex boson. I should have said it before. We are doing complex boson just for the convenience. And if you to find the dimensions of these operators which create this twisted boundary conditions, you can. There is formal methods. There is a known twist operator for this. It has some definite OPEs. But to just calculate the dimension of that, it is very easy. You just quantize this boundary condition and find its 0 mode, 0-point energy, and that shifts. And the shift is the dimension of the operator because it acts on the vacuum to create this state. And the shift of this is, so dimension, okay, so let me write dimension of the operator, twist operator, is half of k by n 1 minus k by n. You can calculate it. People who know it, we can just go ahead and calculate it. This is what the shift it is. So, but we have to do all the twists basically. You know, there are all these n copies, and all of them are twisted by k, and k is running from 0 to n minus 1. So you have to consider the product. So the full twist operator, tau n, is product k is equal to 0 to n minus 1, tau k. So the dimension, you see, is summation k is equal to 0 to n minus 1, half of k by n, 1 minus k by n. So you can do these sums. If you want, you can do these sums and convince yourself that the answer is 1 by 12 n minus 1 by n. And this is delta n for c equals 2, which is what is expected answer for this. Okay. So basically you have to insert these two twist and anti-twist operator and compute it, its 2-point function. For the fermions, the twist operator can explicitly be given in terms of the bosonized variables.
For a real scalar, what do you do?
Yeah, real scale, yeah. I think there's something called Ashkin-Teller for n equals 2. So I don't know what else, otherwise. For n equals,
But
2.
the answer is the same?
Answer is same, yeah, so half of, it actually, yeah.
So maybe I just add a scalar and
It could be.
What does it mean to have a twist operator for
Real, because
go around, you can't
No, but I'm just saying that entanglement you can start doing.
certainly compute, yeah.
So, I mean,
Yeah.
maybe you can't do this thing of mapping to
This basis, yeah.
This is the
yeah.
Complete, yeah.
That's, yeah.
Yeah, this is called as Ashkin-Teller. Fermion. So psi 1 plus I psi 2. So you bosonize to a compact boson. So this is a compact boson. And twist operators, say of, if you twist it by k by n, like 2 pi k by n, I think people who know string perturbation theory will know that this is the operator you have to do to twist it. And the dimension of this weight operator is k squared by n squared. Half k squared by n squared is the dimension of this operator. And you have to construct, so if you actually see the eigenvalues of this with a minus sign, it's quite tricky. So if you calculate the eigenvalues of this minus sign, you'll have to actually compute. So the eigenvalues is k is running from, so it can run over half integers, steps of unity. So if n is even, for instance, it's running over half integer. So the eigenvalues with that minus sign, if you calculate the eigenvalues, they run from this. And if you sum over, you can do this, you have to do it carefully a little bit. You can do this sum. 1 by 24, because 2 n by n, which is what is the expected answer. So there is, of course, there is a general argument of finding this dimension irrespective of any CFT. I just want to say that it exists, and it basically relies on some uniformizing map, which maps this whole complex surface to some plane. Okay. And using some conformal transformations and all, we can actually find this dimension. So maybe I wouldn't sort of indicate it, but there is an argument which gives this dimension of this operator for a general CFT. So of course, given this answer, you can go to other geometries related to this by conformal transformation and keep calculating it. So as we just discussed, the entanglement entropy or Renyi entropy in this case, n is also there, does not depend on the details of the CFT, just the central charge. There are, as we discussed, perturbations from this answers are known, semi-infinite line answers are known, and so on. There are many cases in which things are. 2 intervals, yes. So that is also known. 2 intervals answers are known, which for free theories, yes. And there is general CFT recently. I don't think I'll have time. So there's an argument by Hartmann recently for large C. Large C, how does it behave? There's an argument actually. And to compute that large C behavior, the equations one goes through is very similar to the holographic equations. It's exactly identical actually, how to evaluate that. I don't think I will have time, but I will systematically go towards that.
So you mean in the factorization limit?
The large C limit actually.
Large C limit.
Large C limit,
Is
yeah.
the 4-point function sort of factorizes?
It sort of factorizes, yeah, it actually factorizes there. The identity is what is propagating in between when we factorize it. And there is a way you can extract out the large C behavior that relies on some monodromy equations, some kind of equations. So, yeah, let me just go ahead systematically, I think, yeah. And to do it. So one of the things is that if you, even here you can see that, just to indicate, maybe Anindya will mention, if you do this Renyi entropy, differentiate it at n equals 1, you'll see that it's proportional to the central charge. Everything was proportional to the central charge. Here it's trivial. So if you differentiate the Renyi entropy, and set it to 1, you get the central charge. It's proportional to the central charge, which is observed in the higher dimensional case for spherical entangling surface, recently again by Perlmutter, I think. So again, now let's do two intervals. So I will, I don't think, yeah, so.
So what is the claim that it's always proportional to
Central charge, yeah, always, the general argument in a higher dimensional CFTs also. If they, for that, I think he uses spherical entanglement surface, for spherical entanglement surface. It is basically proportional to the TT correlator, stress tensor correlator. In the general CFT, you say it that way.
But it is only for spherical surface.
Spherical surface. That has been proved for spherical surface.
For cylindrical surface is also the holographic computation suggests C.
But not in general.
So let me go ahead to the two interval case. So here conformal invariance plays very good role actually, important role. So entanglement for two disjoint intervals.
Sorry, space is S1.
Yeah.
What happens when space is S1?
When space is S1. Yeah, that's the cylinder. You can map it to the cylinder. You can take the plane and map it to the cylinder.
In that case, I need another boundary condition for S1.
Yeah, yeah.
Then it does this state.
Yeah, no. These things, the weights of the operators don't. They are local information.
Okay.
They don't change.
So
Actually.
what's changed?
So like for instance, this will become sine. Sine. This is sine hyperbolic for the cylinder. If you do it on a sort of something like this, okay, infinite here, but you take two intervals here, okay, it will be sine. The answer will be sine, not, sine, not 1 by the distance, but distance, that's sine, 1 by sine pi L or something.
And no, does this depend on boundary condition for,
Yeah, this is, I'm putting periodic boundary condition because that's how the sine is coming. Yeah, periodic boundary condition. So, so Renyi entropy for disjoint intervals. So we have basically two intervals. So we have A, B, C, D. So U1, V1, U2, V2. So these are our intervals. And we are computing trace of rho to the n. So now we have a formalism. We insert 4 twist operators at each of the points. So basically tau n u1, tau bar n v1. As anti-twist to remove the twist, tau n u2, tau bar n v2. Okay. Each of them have dimension c by 6 n minus 1 by 4. So delta n is c by 6 n minus 1 by n. Okay. So the answer, of course, conformal invariance, using global conformal invariance, you can reduce this expression. So you can reduce this expression to the following: u1 minus u2, v1 minus v2 by u1 minus v1, u2 minus v2, u1 minus v2, u2 minus v1 to the power 4 delta n times the function of the cross ratio. Okay, so this is by general conformal invariance. You can map it to this. This is general. I think people who know conformal field theory know this answer. So this much you can say first. Okay, so Fnx is basically the cross ratio. Let me write it out. U1 minus V1, U2 minus V2 by U1 minus U2, V1 minus V2. And let me also write 1 minus x. It's good to remember this. U1 minus V2. So you can say this much. From this much, actually, we can say quite a lot of the answer, quite a lot of information about the answer. Yeah, so 1 minus x is this. So this is the cross ratios. So just from this x and x bar, both are there. Just from this much information, the lot of properties of this answer can be said. So let me say first general properties first. Before actually doing it for some specific cases. So the general property, again, we saw this. So these are disjoint intervals. And suppose you use the strong subadditivity, the subadditivity. So we know that SA plus SB, so these are the two intervals, is greater than or equal to general properties. Is greater than SA union B. So that's basically the interval of first interval plus second interval, and A union B is because A union B is what we are computing. This is A union B. This is the answer for A union B. So therefore, this motivates us to construct another quantity. So it's called this mutual Renyi information. This quantity. So AB is the interval. So now I have put it as interval. Sorry. So let's construct this quantity. Okay. So because this is greater, so let's see the difference. I mean, this is one of the simplest thing to do. First thing, and what you can show first is that this one, okay, when you compute it for the Renyi case, this one is just a function of the cross ratio. It's independent of the first numbers, actually. You can see that quite easily. The cross ratio, f of x. So there is this general thing which from scaling analysis you get. And then there is this, so if you take this difference, this thing disappears, actually. So you can see that, actually. In fact, there are many nice things that cutoffs also disappear. So if I compute 1 minus n I nx, which is what you have to compute, if you see this one is minus c by 6, because you know the answer, log of u1 minus v1 by a, minus... Yeah. I mean, yeah, so, so here, for instance, this is calculated without anything. There is, this A comes here. Here, this A comes, just independent, single intervals. These are single intervals. You calculate that. That has an A. This has an A. That, you can organize, put A and A. And this, the things cancel. So V1, this one will cancel with this. And the next fellow will cancel with this. And this is 1 minus x. This object is 1 minus x, actually. You can see that it's 1 minus x. Downstairs in the denominator, it's 1 minus x. So therefore, all that part cancels.
The cutoff cancelling is just because they are disjoint and the very short distance correlations of AB union CD are the same as AB and
CD. Yeah, that's the thing, yeah. Right. So this cancels, you can see it cancels, and if you compute it, I hope people can see that, it cancels. These things cancel. This U1 minus V1, this is U2 minus V2, you can see, and that comes an appropriate way to cancel it. So in fact, the answer is C by 6 n minus 1 by n log of 1 minus x plus log of f of x. It's the cross ratio. Okay. So it's a function of only the cross ratio. That is one of the things. And you can say that, so from the fact that, entanglement entropy of A and its complement, so for pure states, we are doing at 0 temperature, so is the same. You can actually arrive at, maybe I will just state it, but it's very simple actually. You just have to exchange V1 to V2, and you can show that, so exchanging V1 to V2, and also you can, just from the fact that these are all the same operators, and exchanging V1 to V2, or from the fact that the entanglement entropy of the intervals and its complement is the same, you can show that actually f of x has this property. So using SA is equal to SAC. So interval and its complement. It's just like exchanging V1 and V2. We are exchanging V1 and V2. So we calculate this and this correlate. So it has this property, f of x and f of 1 minus x is the same. Therefore, there is a relation. It's a nice relation. Sn in 1 minus x is the same as in x plus c by 6 n plus log. You can write n plus here, 1 minus x by x. So you can write this relation actually, which relates the two halves. So 1 half is enough actually. So one of the things about this, I forgot to mention here, is here you see that the answer really depends on the details of the CFT. So because this cross ratio, it will have a definite expansion, so it depends on the details of the CFT, not just the central charge. And also we know that f and x has a sort of, so you can say something about x going to 0 also. So in CFT, x going to 0, the lowest operator, lowest dimension operator, if unitary, is just dimension vacuum, it's dimension 1. Okay, so basically you can show that because I and x is like this, at x goes to 0, fn, limit x going to 0 is 0. Okay. And CFT, by this expansion, fn x is an analytic function of x. That's another thing actually. And but if you do, why I'm mentioning this is if you compute this by holography, it won't be an analytic function. The leading answer is not an analytic function of x. But in a CFT fn, this I and x is analytic function of x. And using again subadditivity, strong subadditivity, you can show that it's actually an increasing function of x. So that's another property, increasing function of x. Okay. So let me, I have that, but you can show that for using SSB, I and x is function of x.
Map the whole thing into some conformal transformation to bring it on top of each other, right? To some, so that it's an increasing function of x.
Yeah.
You fix 3 points at the same.
Yeah. So.
3 points fixed and then you look at a function of the 4 points.
Right. Yeah. Yeah. Or 0x and infinity and you move x.
Yeah. 0 1 and.
You move x. Yeah. So it's basically comes from strong subadditivity. So if one of them is a subset of the other, B is a subset of the other, you can show. There are some relations you can use and show. I won't show it, but there is. You can just manipulate it. Move the other one. Yeah. And for free boson CFT, in fact, this can be calculated. Free boson CFT, In can be calculated, or the trace of rho to the n can be calculated. And let me just write the answer just so that you have one answer to stare at with. So these are the general properties. So this contains, so the crucial thing about this is it contains information about the CFT. So for free complex boson CFT, if the boson is not compact, for a compact there is a very nice answer also. So basically the 4 twist operators and fnx. So I just have to give you the formula for fnx. It's basically some hypergeometric function. You can see the symmetry of x going to 1 minus x here. So fnx is this, and fk nx is this hypergeometric function. It's this hypergeometric function. So that's the answer for this.
I'm sorry, I
Yeah,
missed
yeah.
something. How did you, are those formulas true for a general CFT or what?
Which this one?
1 minus n.
No, this is for, of course, for this interval. For the 1 plus 1, 1 plus 1.
No, 1 plus 1, but you have
This-
2.5. Oh, in terms
Yeah.
of f of x.
This guy is sitting there, yeah. This guy is sitting. But that relation in x and in minus x, I think it doesn't have f of x. It doesn't have f of x.
Or rather,
It cancels. F of x and f of 1 minus x is the same. So if I take in x, so there was a relation I wrote, I forgot, I sort of went systematic. And minus x, that is related without f actually. You can see that. So because fx and fx and f1 minus x is the same. So if you take the difference, the answer is this: in 1 minus x is in x. Did I write that? Oh, I wrote it and I erased it. So plus c by 6 n plus 1 by n log 1 minus x by x. So the f disappears because you take this, put 1 minus x. So this is x and this is 1 minus x. F of x is same as f of 1 minus x. So if you subtract them, you will actually get this relation.
sorry,
Yeah.
what is that, the line, after you define in,
In,
you
yeah.
can write 1 minus n in, that formula.
This one.
No, the one above it.
Yeah.
That's just what you got.
Oh no, I didn't complete. Sorry, I didn't complete. So this I should write this one minus c by 6.
Okay.
This and
That's
then
the
this.
first
Yeah,
term
yeah.
you wrote of
Yeah,
SN
yeah. So this is that. Then this is the next one, and then you have to substitute.
And then the net result is this.
Yeah.
Okay.
Sorry, this
No,
equation.
that's okay.
Yeah, I just have to substitute that. Yeah. So that's the thing. Right. So this is the answer. So and f and x. So one of the things which are recently, maybe I'll just indicate it recently. So f and x is known. The expansion of f and x as powers of x is known if you assume that the operator, the lowest dimension of an operator is 1 and something else, some h. So f and x goes like this. These are the recent checks. I mean, this f and x admits an expansion like, the first order term. So of course it starts with some 1 or something. So minus some, so n. So the leading term, suppose there is a leading operator of dimension, the lowest dimension operator is h. So this is Cardi and Hedrick. Cardi, Calabres, Hedrick. H. So H is the lowest dimension operator. So f and x is known to this first term. It is known. There is some expression. You can compute the entanglement also. I mean, take the derivative and take 1. And recently this has been computed.
H is the lowest dimension operator after that.
After the identity. There is an
And then corrections are involving
higher powers. Higher powers.
High powers.
Higher powers of x. So this, so if you know a little bit of the matter content, suppose you say that this is the matter content of the CFT, and this is the lowest correction, you can actually, and you try to do this in the bulk, and it has been reproduced actually in the bulk also by this recent work of I think this Faulkner and Hartnell and all. They have reproduced this term in the bulk. They did it for the stress tensor. They assume it's a stress tensor. Yeah, they just assume there is a stress tensor. So you have to compute one loop determinants around that geometry, that replica bulk dual to the geometry, and they have got these kind of results actually. So, but what is the leading order answer? I didn't say holographically. What would like? I mean,
I'm not sure exactly. Why do you expect that the bulk will reproduce it exactly? Meaning,
yeah, I mean it's one loop correction somehow.
What is the ADS CFT correspondence?
No,
I mean-
it says correspondence, but the model it says non-C.
Yeah, but somehow this one loop correction
Yeah.
is like just calculating the matter content. I mean, what is just the sort of matter
So you are
content?
saying it somehow goes beyond large C.
Yeah,
Or
this,
one
yeah,
plus
1 plus 1, yeah, CFT. Yeah, I mean, just the one loop correction. Like you put in this much matter, and you say that this is your matter content in the bulk.
So I didn't understand, sorry Ashok. I thought you were saying, without making any other assumption, if the lowest dimension operator after the
Yeah.
identity has dimension
Yeah.
x, then f and x has this
This
expansion.
for expansion.
So that would apply to a large C theory.
Yeah, yeah,
also.
it would apply to a large
And
C.
then let's assume that the large C theory has a gravitational
Yeah,
dual
yeah.
with
Yeah,
low
so
line-
in the large C theory I can understand.
Yeah.
So you can, if you say this is reproduced in the bulk in large C limit, but the question is whether there are 1/c corrections which you don't see from the bulk theory.
Yeah,
Meaning,
okay,
is it that
okay.
in the bulk theory you get this up to 1/c corrections which you don't know, or is it that you get it?
Yeah, I mean, you just put it actually. In bulk, you have to assume that this is the matter content.
No,
I mean-
I think, isn't it, I thought Hartman's paper says that up to, I mean, at the level of x to the power h,
X to the,
script,
this is it, yeah.
then all the other dot terms, they have the 1/c
C corrections.
As a result,
So,
this
okay.
you will reproduce from
These are
Yeah.
the 1/c
Okay.
corrections.
Yeah, this doesn't have 1/c. This is a one loop term. Yeah, yeah, this
It's
is
from the bulk,
yeah.
from the CFT.
CFT.
But
This
as
is
from the bulk side only do. So you are saying that there is a 1/c correction to this.
not at the level of x to the power h. I think it has
Yeah.
higher order stuff.
okay. So maybe I think I should just stop. I mean, it's 6 o'clock actually. The thing is, there are some personal reasons I have to go back soon actually, because some shops close and I have to do something. So I don't know. I mean, so, yeah, I think I'll stop actually. Yeah, because I have to buy something for going home. Yeah.
That's it, decided. He makes us decide.
I can give some small little thing in the next class actually. In the next class, yeah. In the next tomorrow, I can give a small little part complete. Okay.